Good morning, everyone. My name is Aninda Swarnaker, and I am pleased to present our Engineering 990A project, which I completed in collaboration with Sir Nahian Preonto under the supervision of Dr. Ashraf Ali Khan. The title of our project is Comprehensive Analysis of De-Icing Technology for Wind Turbine Blades, Mechanism, Modeling, and Performance Evaluation. In this presentation, we'll explore the problem of ice accumulation on wind turbine blades, particularly in cold climate regions like Newfoundland and Labrador, and how it affects turbine efficiency and reliability. We are focused especially on the electro-impulse de-icing method, which uses electromagnetic pulses to break ice bonds without relying on thermal energy. Our goal was to study how effective this technique is compared to other de-icing strategies through simulation and modeling using COMSOL multiphysics. Wind turbines operating in cold climates face a serious problem, that is ice formation on blades. This ice drastically alters blade aerodynamics, increase drag, decrease lift, and ultimately reduce the power output of the turbine. Beyond efficiency losses, icing introduces safety risk due to ice throw, forces unplanned shutdown, and accelerates mechanical wear due to rotary imbalance. For example, even moderate icing can cause the system to misinterpret data, actively activate emergency stops, or trip vibration alarm. Our project addresses these challenges by first analyzing how ice affects turbine performance aerodynamically and operationally. Then we focuses on evaluating electro-impulse de-icing or ED as a promising technology that removes ice using electromagnetic forces rather than traditional heating, making it more energy efficient and potentially faster. We model and simulate the ED system in COMSOL to gain insight into the physics of Lorentz force generation, magnetic field distribution, and their mechanical impact on blade-mounted ice. Next, what sets our work apart is the multidisciplinary approach we use to understand and simulate ice mitigation. First, we conducted a detailed performance assessment showing that how aerodynamics properties, especially lift and drag forces, are altered under ice condition. Next, we designed and simulated the ED system in COMSOL using both electromagnetic and thermal modules. This allows us to visualize how magnetic pulses behave in real turbine materials and how these forces can be used to remove ice without thermal melting. Finally, we investigate the electromechanical behavior of the system, particularly focusing on the generation of Lorentz forces and how these forces interact with the blade structure to detach ice. While many previous studies focuses only on heating-based system, our work contribute new insight into non-thermal, pulse-based ice removal, and combination of both and its real-world feasibility. Ice accumulation does not behave the same at all wind speeds. Interestingly, data shows that as wind speed increases from 2 to 4 meters per second, the icing thickness increases by about 117%. A dramatic jump in just a 2 meters per second changes. However, beyond this point, although the mass of ice continues to increase, the rate of thickness growth slows down. This might seem counterintuitive, but it makes sense when we consider that at higher speed, the droplet may spread over a large surface area or bounce off before freezing. The figure on the slide shows how both icing mass and thickness vary with wind speed. These relationships are important because they influence when and how we activate de-icing system. If we understand the critical wind speed where icing is most aggressive, we can preemptively respond with more efficient ice detection and mitigation strategies. Temperature is perhaps the most crucial factor in ice formation. From our analysis, when temperature drops from -1 degree Celsius to -2 degrees Celsius, icing mass increased by 71% and thickness increased by 24%. Interestingly, as the temperature drops further, say from -2 degrees Celsius to -5 degrees Celsius, the rate of increase becomes smaller. This means most dangerous icing happens just below freezing, where the water is supercooled and highly likely to freeze upon contact. These results are shown in the graph to the right. As temperature decreases slightly below freezing, both mass and thickness rise quickly, but then the slope flattens. This information is critical for de-icing system because it tells us when to be most alert and active. We can design intelligent control system to initiate de-icing when temperature hover around -1 to -3 degrees Celsius, which is where ice buildup is most aggressive. Icing not only changes blade shape, it directly affects energy production. As a blade accumulates ice, their shape becomes rougher, which decreases lift and increases drag forces. These changes result in less aerodynamic efficiency and ultimately less power generated for a given wind speed. In fact, in real-world conditions, turbines in cold regions can lose up to 30% of their annual energy output due to icing. This has huge economic consequences, especially for remote northern communities that rely on wind power. Moreover, icing can cause turbine to reach rated power at higher wind speed or fail to reach it at all. In one study, power output dropped by 37% during icing, even though wind conditions were otherwise optimal. These losses highlight the urgent need for effective and reliable de-icing technologies, especially those that minimize power consumption during operation. To quantify these performance losses, we developed mathematical model comparing clean and iced blade condition. One of the key findings is that icing reduces the lift coefficient slope by about 30%, meaning that for each degree of angle of attack, the blade produces significantly less lift than it should. Additionally, icing causes an early stall, which is the point where airflow breaks down and lift collapses. This restricts the turbine usable operating range and makes it harder to capture energy efficiency. We also noted that the lift to drag ratio drops, indicating overall aerodynamics performance is much poorer in ice conditions. These results are consistent with published literature and shows why turbines under icing need external intervention, whether through blade design changes or active de-icing system. In this slide, we show a simulated comparison of blade performance under clean and iced conditions. The clean blade follows a predictable lift curve, gradually increasing lift with angle of attack until stall occurs. However, the iced blade shows a lower maximum lift and stall occurs at a smaller angle. This indicates that even a thin ice layer significantly alters the pressure distribution and flow separation over the blade, making it unstable. The simulation reinforces the idea that icing is not just a minor inconvenience, it is a major aerodynamics disruptor and that degrades performance across the entire wind speed range. This simulation forms the foundation of our decision to evaluate de-icing system, particularly ED, which we simulate and analyze in the following section.
Detecting ice formation on wind turbine blade accurately and promptly is essential for reducing performance declines and preventing potential structure harm. So for ice sensing mechanism, we have two types of strategy. One is indirect method and one is direct method. So for indirect method, we can use the predictive analysis, and for direct method, we have capacitive sensors method, we have optical method, we have ultrasonic method, where ice is detected through vibration, variation in sound wave propagation. They are effective for thicker ice layer but are vulnerable to noise interference. So then we have microwave high sensing technique, and then we have flexible sensors and the modern integration with ML and SCADA for real-time monitoring. And so, and now in terms of de-icing technologies, we have two types of de-icing technologies. One is active and another is passive. So they includes the electrical heating, or we can say thermal heating. So it is the most common and effective techniques. These include internal electrical heating elements embedded within the blade and external heating films applied on the blade surface. Heat is generated via a resistive element powered by the turbine or grid, melting the ice or weakening the adhesion. And then we have then ultrasonic mechanism, so which employs high frequency mechanical vibration to break apart and detach ice. This system can effectively address thin ice layers and can be embedded in certain section of the blade. Although their long-term performance during operation is still under study. Then we have electric impulse de-icing technique, where we will gonna briefly high voltage pulse introduce. We're gonna introduce high voltage pulse through a coil, creating an electromagnetic force that separates the ice from the blade. This method is efficient in terms of energy and act quickly, but requires dependable integration to the blade design. So here we have a comparative analysis between the different de-icing techniques. So we can see that the table is divided by the techniques, the name of the techniques and their principle, their energy use, the effectiveness and integration complexity, which is a major part of this system. So in terms of electric impulse, we can see the principle is by magnetic shock pulse, and their energy use is very low, their effectiveness is very high, and the integration complexity is high because it depends on the blade design too. And for the ultrasonic vibration, so the principle is acoustic vibration. The energy use is low, the effectiveness is moderate, and integration complexity is moderate too. So for mechanical actuators, so the energy use is medium, whereas in the intelligent hybrid system, the energy use varies and the effectiveness is high, but the integration complexity is also high. So our goal is to apply one of the method uh, to see how the impact of our method applying in terms of ice breaking for wind turbine. So we'll be using the electric impulse de-icing technology, and with the principle of it is from DC power, then the capacitor, and the capacitor will gonna then we're gonna turn the coil and then generate a pulse. So in in that case, there will be after that a magnetic field will be induced that will have eddy currents and that will apply Lorentz force. And due to this vibration, ice will gonna break. So it uses high current pulse to generate Lorentz force and coil embedded in blade, which implies electromagnetic impulse and thus ice detachment. So we used Comsol multiphysics to apply to actually simulate our idea to see what's the actual effect of applying Lorentz when we apply Lorentz force to a surface and how it reacts with the electromagnetic impulse and everything. So we choose a aluminum plate. On top of that, we put a coil, a copper coil, and then using the Lorentz force, we will gonna apply a frequency domain, 60 hertz or 60 hertz magnitude, and we will try to figure it out what's the result. So here we can see this plate and the coil is all meshed up. The finite element mesh of the aluminum plate and copper coil assembly used in the electro impulse de-icing simulation. It is a high density mesh around the coil that ensures accuracy. So in this picture, we're seeing that this is a simulation result, and we can see the magnetic field inducing around the coil, and the peak magnetic field is 3.7 to 10^4 Tesla at coil center. So it contour depicts the distribution of magnetic flux density created by the copper coil across the aluminum plate surface. The field is concentrated around the coil region, generating a near circular high intensity zone. The symmetric field pattern implies homogeneous magnetic excitation, which is necessary for generating the Lorentz force needed to break the adhesive binding of ice on wind turbine blade surface during de-icing. So this is the impact of Lorentz force, where we can see in the picture the peak Lorentz force is 40 Newton per meter square meter cube, is concentrated directly beneath the copper coil where eddy currents interact with the transient magnetic field. Localized mechanical impulse effectively detach the ice from the surface by breaking adhesion without relying on significant heating. And the spatial distribution of the Lorentz force generated due to the interaction between the transient magnetic field and the eddy current within the aluminum substrate. The force is concentrated in the region beneath the copper coil. So, and this is in this way, it actually effectively detaches the ice and fulfill our purpose. So in this graph, we are seeing this is the variation of magnetic flux density distribution along the arc length beneath the copper coil. So from this graph, we can see that the peak magnetic flux is 3.68 × 10⁻⁴ Tesla. So, and the strongest field region is central zone under the coil. So it actually provides high eddy current induction that occurs in this region of maximum magnetic interaction. So, so the thing is, after this, the application inside would be this zone correspond to maximum Lorentz force generation, which is very crucial for efficient ice detachment through induced eddy current in the aluminum plate. So, in terms of our future work and conclusion, we can tell this research investigated the aerodynamic, mechanical, and electrical factors associated with ice buildup on wind turbine blade, emphasizing its significant influence on power generation. A comprehensive assessment of sensing technologies and de-icing method, ranging from thermal and understanding to cutting-edge electroimpulse system, highlighted their respective advantages and drawbacks. The simulation of the electroimpulse de-icing method using COMSOL demonstrated its promise as a rapid, non-thermal, and energy-efficient option for ice removal. So this process shows potential for fast, energy-efficient de-icing, and the COMSOL simulation confirms the effectiveness of it. So future research will aim to improve the integration of sensor-driven feedback with intelligent de-icing control system, and also if we can introduce this to a hybrid system integration and for real-time control. And our next plan is to implement a battery system management for self-sustainability of the wind turbine under the de-icing management. So we would like to thank our supervisor, Dr. Ashraf Ali Khan, for effectively guiding us throughout the project, and a special thanks to our project coordinator, Dr. Mohsin Jamil, for pushing us to achieve a good quality of work, which is very necessary for this kind of project. So we sincerely apologize if we done anything wrong, and yeah, and for the support, thank you.